Today's lesson is on probability, which is the likelihood at a given event could occur. And that could be rolling a die, spinning a spinner when you're playing a game, flipping a coin, or even chance that you may get rain or sunshine on a given day. There are three methods of determining a probability. And very often we'll blend these different approaches. Empirical probability is by experimentation. We flip the coin and we see how many times we get heads and how many times we get tails. Theoretical is using known elements. For example, we'd expect a coin is going to be half the time heads and half the time tails. When we're rolling a die, we would expect, if it's a six-sided die, that 1/6 of the time we get each of those numbers. Or there's also subjective, which is where you're making assumptions. Like, for example, you're trying to tell the weather. All right, I think that there's a 60% chance that we're going to get weather in a given area on a given day. Probability components include the experiment, which is the activity, again, which let's say activities we're flipping a coin, that's the experiment. The sample space is possible outcomes. If we're rolling a six-sided die, the outcomes could be the numbers 1, 2, 3, 4, 5, or 6. If it's heads or tails, that would be either heads or tails. The event is the subset. Whatever do you get? Did you roll a 1? Did you roll a 2? And the outcome is just that, what you got. The result, did you roll a 1, a 2, 3, 4, 5, or 6? So what's the probability that you toss a coin and it lands heads up? Well, your experiment, all right, is actually flipping the coin, right? Your sample space is, in this case, we'll draw a probability tree to represent those examples. It could be a possibilities, it could be a H, or it could be a tail. So your sample space is, in this case, 2. The event is the actual flipping of the coin. Do you get a 2? Do you get a heads, or do you get tails? And the outcome, in this case, is heads. A probability is a way of communicating a belief that an event could occur. We express it as a number. It has to be between 0 and 1. Okay. So when you hear athletes or coaches saying they're giving it 110%, in strict math terms, you can't be more than 100%. All right. It has to be a number between 0 and 1. It could be 0, it could be 1 if it's definite. We could write it as a fraction, we could write it as a percent, as a decimal, or we could even write it in terms of odds. Again, the total probability of all possible events has to total 1. So half the time heads, half the time tails, half plus half gives you 1. The relative frequency is the number of times that an event will occur divided by the number of opportunities. For example, right here, if we say here that we're flipping a coin, well, the number of times, let's say we're doing heads, right? So F is going to be, our X is representing heads. So N is the likelihood that we're going to get, X represent heads. So what's the chance we're going to get a head? Well, there's one possibility of getting a head. Out of the total number of opportunities is 2. So our relative frequency is going to be half. Half the time we would expect heads and tails. Where Fx represents the relative frequency, N of X represents the number of events, which in this case 1 heads, and N represents the total number of events, which is possibilities, which is 2, so half the time heads. Again, it has to be a number between 0 and 1. We can write it as a half, we can write it as 50%, we can write it as 0.5, or we can write it as 1 to 2 odds, either way. If we were to add up half for heads, half for tails, again, they have to add up to 1. What's the probability of a coin landing heads up? The exact problem that we just walked through. All right. Well, how many desirable incomes are there? Well, desirable incomes, there's going to be 1, right? Because there's 1 chance of heads. And how many possible incomes? Again, we'll draw a probability tree. The number of desirable outcomes is going to be 1. All right. The possible outcomes, well, it could possibly be heads or tails, so 2. So again, we get 1 over 2. Or 0.5, or 50%. So what's the probability of a coin landing tails up? All right. Obviously, that's also going to be 1/2 as well, right? Half the time heads, and we'd expect half the time tails. What's the probability of a coin being tossed twice and it landing heads up both times? Well, how many desirable outcomes are there? So here we're going to have 1 set of trees. All right, and then we're going to have another set of trees for the second flip. All right. Well, how many desirable outcomes? Well, there's one desirable outcome, heads, heads, right? Okay. So there's only one desirable outcome. Well, there's 4 possible outcomes. 1, 2, 3, and 4. So the possible outcomes is going to be 4. So our probability is going to be 1 divided by 4, or 0.5, or 0.25, or 25%. What's the probability of tossing a coin 3 times and then it lands heads up exactly twice? First, we're going to do it using trees. So we're going to have one tree, another tree, and yet another tree, because we're flipping our coin 3 times. All right? So how many desirable outcomes are there? Well, first we'll look at heads, heads, heads. Is that desirable? No. It lands up heads 3 times, so we'll cross that one out. How about heads, heads, tails? Well, is that desirable? Yeah, that's landing heads up twice, so that works. How about heads, tails, heads? Well, we got 2 heads, so that one's desirable. That one's good. How about the next one? Heads, tails, tails. Nope, we've only got 1 head, so we'll cross that one out. How about tails, heads, heads? All right, that's fair because we got 2 heads, so that one works. How about tails, heads, tails? Nope, we only have 1 head. Tails, tails, heads? Nope, only 1 head. Tails, tails, tails? No heads. So we got 3 desirable outcomes, and how many possible ones? 1, 2, 3, 4, 5, 6, 7, 8 possibilities. So 3 out of 8. Okay, we do the math, plug it into a calculator, and again, you can use calculators on all your quizzes, tests, and homeworks, and it's 0.375 or 37.5%. Now we're going to take that same problem we just did using trees, and we're going to do it mathematically using a formula that's in your formula sheet. The formula is going to look a little scary, but I'll walk you guys through it. Notice, just keep in mind, right now we got 3/8, so we should end up with 3/8 when we do that as well. This way we did it right now with trees works fine for 3 flips. But what if I had 100 flips of a coin? Then that would take way too long, which is why we need to learn, which is why we come up with formulas, because it makes it a little bit easier when we're dealing with big numbers. All right, first, let me introduce a binomial process. Binomial process is a trial that has 2 possible outcomes, a yes or a no. Do we get ahead, or do we get yes, or do we not get ahead? No. Okay, on, off, or right or wrong. All right, in this case, the trial outcomes are independent. When we toss a coin, it doesn't affect future time tosses. Future coin tosses, I'm sorry. Something that's not a binomial process, we're not going to look at it today, we'll look at it next time, is playing cards. Because if I flip over 1 card of the deck, the chance of me getting an ace is 4 out of 52, because there's 52 cards in a deck. But after I flip that 1 card once, now how many cards are left in my deck? Well, I don't have 52 cards in the deck. I only have 51 cards in the deck. So my trial outcomes are not going to be independent. So flipping a coin is independent, but playing cards is not, because every time you take away 1 card, your odds are changing. Okay, all right. And when you grow up, if you ever to try, to play poker or something like that, that's why card counters can do well, because they can use those odds to their advantage. Now this formula, as I mentioned, we're going to do that same calculation we did before, and we're going to get the same number. We said, what was it, 3/8, I think it was. But it looks a little scary, okay, but it's not. So P stands for probability, all right? X is the number of times for a specific outcome. Well, we're looking for 2 heads, so our X is going to be 2, all right? So right here, this number right here, it's going to be P sub 2. So for our numerator, it's going to be X factorial, so that's going to be 2 factorial, right? Okay? All right, and here this is P to the X power, so this is going to be 2P squared, all right? And we'll do the N, we'll deal with N next. N is the number of trials. Well, we're flipping a coin 3 times, so our trials are 3. So we'll plug 3 in anytime there's an N. So here we've got our numerator is 3, so that's going to be 3 factorial, right? Oops, I forgot to write the factorial down here. Okay, now we've got N minus X. Well, N is 3, X is 2. 3 minus 2 gives us 1, so that's going to give us 1 factorial. All right, and N minus X is 3 minus 2 gives us 1, so here we're raising it to the 1st power. All right, so again, scary formula, but not so hard. We've got 3 factorial divided by 2 factorial times 1 factorial. I'm assuming you guys are familiar with factorial in terms of math, okay? If not, if you don't remember, we'll go over it in a couple minutes on the next slide or two. Okay, so P represents the probability of success. Well, probability of getting ahead is a half. So so that P is a half. So right here we've got a half. So what we've got here, P raised to the X means we've got 1 over 2. We raise that, we square that, so that's 1 over 2 squared. Probability of failure is a probability of not getting ahead, which is also 1/2. So Q in this case is a half. So what makes this a binomial process is we're only dealing with P's and Q's. If it was P, Q, R, then it wouldn't be in binomial. We couldn't use this formula. So in this case, Q is a half. So Q raised to the first power, so it's 1 over 2 to the first. It's supposed to be 2 squared. So we've got 3 factorial over 2 factorial times 1 factorial. All of that times 1 over 2 squared times 1 over 2 to the first. Now, this whole formula here, in a statistics class, you may have learned how to use this button on your calculator, NCX. If you know how to use that, you can skip a lot of this stuff, okay? And if you know how to use that on your calculator, that's fine. You can skip it. But this is a shorthand that you may learn from, if you take a statistics class. We spend a couple days or a couple weeks or so on this kind of stuff in statistics. Obviously, they spend a lot more time on it. What's the probability of tossing a coin 3 times and getting it heads up 2 times? Again, this exact same example, same formula that we had, right? Well, this is the same stuff we just wrote on the last slide. 3 factorial, all right, n is 3 chances. So 3 factorial means 3 times 2 times 1, okay? X factorial, x is 2, so x factorial means 2 times 1. So factorial means we keep multiplying that number by the number 1 less than that until we get down to 1. All right, and then we've got P is a half, so half squared. Q is a half, so it's half to the n minus 1, which is a half. So that's how, this is what, same numbers that we just calculated out on that slide. And we get a probability, we plug it into a calculator, we get 0.375 or 37.5%. So again, notice we get the same results whether we use this formula or we use the tree. The tree initially may be a little bit easier, but again, what if you're trying to do 100 or 1,000 coin flips? That, in terms of trees, that would take forever, whereas it still would be tedious doing factorials with this, but it certainly would be easier than trying to do all those trees. All right, the law of large numbers says that the more times I conduct a trial, the more times I flip a coin, the closer the results will come toward a theoretical probability. So let's say, for example, I toss a coin 5 times, and my probability of getting ahead ends up being 60%, okay? Then I toss it 500 times, we'd get closer to 50%. In this case, let's say we get 50.2%. So this example matches the law of large numbers in that we expect that the more times we toss our coin, the closer we're going to get to the theoretical probability, which again is 50%.